Hello everyone, today we are going to start section 3, the last section in our chapter magnetism, which is about how to produce electric currents from magnetism. So see, what do you notice from the title? It's opposite of section 2. Section 2 we talked about the magnetic field produced by electric current. We said that if we have electric current flowing or moving in a wire, this current or these moving charges, they will create a magnetic field around this wire. Today we will talk about the opposite. We will see that electric currents also can be produced by using magnetic field or magnetism. Let's see how. So this phenomenon first is called electromagnetic induction and was discovered by Faraday and Henry in 1831. The simple demonstration of this phenomenon, electromagnetic induction, is having girls only a coil of wire, and inside it, let's say, empty. And this coil of wire, it's not connected to any source of electricity, no battery, no power supply, so nothing is providing current. Nothing is providing current. It's only here connected to galvanometer. Do you remember what's the role of galvanometer from section 2? From section 2 we said galvanometer is a device that we use it to detect a current, to see if there is a current flowing or no. So here the needle must be at 0, right? Because what, girls? Because here this coil of wire is not connected to any power supply. It's not connected to any source of electricity, so no current, so the needle should be at 0. But Faraday demonstrated that if he moves the magnet, a bar magnet, only a simple bar magnet, inside this coil, the needle will deflect. What means the needle will deflect? The needle will move to the right or to the left. It will rotate. So the needle deflects, it means it's showing now as a specific number, so it's showing as a reading. So this reading is for what? Is for the current. So by just moving this magnet inside our coil, inside it, we see that the needle shows a current. The galvanometer shows that there is a current now produced. So that's why we call it an induced current. Induced current, it means it's induced by something, it's produced by something, and it's produced here by the motion of the magnet inside it. We will talk about for sure much more details, but now I'm just explaining briefly the demonstration. So observation: when the magnet moves, a current occurs in the coil of wire. How do we know that there is a current? Because this current is just measured by the galvanometer. We are using this device to show us the current. Here another simple demonstration. I have wire. A wire is not connected to battery, it's not connected to power supply, it's just connected to galvanometer. Galvanometer, what is the role of this device? It measures the current in this wire. So the charges inside the wire are at rest at the beginning. They are not moving. There is no flow of electrons, so there is no current, so the needle should be at 0. But if I bring a magnet and I move it here in and up, in and out, I will notice that the needle of galvanometer moves, showing a reading, showing current. Also, instead of moving the magnet, we can do something else. We can move the wire. We can keep the magnet at rest, and we can move the wire up and down inside it. So actually, girls, it doesn't matter which one moves, the wire the loop or the magnet. It doesn't matter which one. The most important thing here is to have relative motion. What is relative motion? Relative motion, it means like an object is moving relative to the other. Okay, now here the magnet is the one which is moving relative to the wire. Here the magnet at rest, but the wire is moving relative to the magnet. Okay, so the most important thing is to have a relative motion. Now concentrate with me. In this video we will understand all the details. Yes. First we will start with a revision about section 2. What you can see here, there is a battery and a wire connected to it, and here a resistor. Okay, so girls, here we're still in section 2. Okay, we are doing a fast revision about section 2.
Hello. Oh.
Who is Oersted? Do you remember the name of this scientist?
Oh.
Huh?
So Oersted is the scientist who discovered that electric current produces what? A magnetic field. See, he just, girls, here connected the wire to battery. Okay, so current is flowing in this wire, and he brought a compass near to it, and we will see what will happen for the needle of the compass.
Oh.
So this is the experiment that we talked about in section 2, that an electric current produces magnetic field. So let's see now Faraday, the one who came to Oersted, what he will do after watching this experiment. He starts to think, like, if electric currents can give magnetic field, can produce magnetic field, is the opposite possible? What did you notice here? When he brought or he moved the magnet inside the coil, the needle of the galvanometer moved to the right. Okay, so it indicates that there is a current. But when he stopped moving it, when he moved it inside and then stopped, okay, the needle will return back directly to zero, showing that no current. So only while moving it down there is current, and we can see it here on the device that measures it, that measures current on the galvanometer. Okay, but by holding it inside the coil at rest, the needle will directly return back to zero. Okay, so now he put the magnet at rest, he held it and he moved the coil. Okay, and he saw the same result. So it doesn't matter which one moves, the magnet or the coil. The most important thing is to have the relative motion. Okay, now girls, what do you notice? When he moved the magnet away, when he moved it up, we can see that the needle of the compass, okay, it goes toward 10, but in the opposite side, the negative side. Okay, so what does this indicate? It indicates that there is a current, because look, it moved to 10. So there is a current with the same value, with the same value magnitude, but how? In opposite direction. So the current produced when he moved the magnet in, okay, was in a direction, let's say to the right, and when he moved it up or away, there is a current produced, but in the opposite direction, let's say to the left. Okay, so here this shows that the motion of the magnet produces current, but not always in the same direction the current is produced. Okay, it depends on the motion of the magnet. If the magnet moves in, okay, so the current will move in a specific direction. When it moves out, the current will move in opposite direction. Okay girls, if you remember, when he moved the north pole inside the coil, the needle moved to the right. But when he now reversed the magnet itself, okay, and moved the south inside the coil instead of the north, we can notice that the needle moves to the left. Okay, so when we reverse the poles also, this process reversed the current moving in our circuit, in our wires. Okay, another thing you have to know it about this electromagnetic induction, this phenomenon, is when you move the magnet up and down faster, okay, you make a faster motion, the needle will move like also faster, right and left. So this means what? The current is producing now at a faster rate.